All right, so for problem number 29, I think this one is, for the practice exam. It says that a 9-meter long 30-kilogram iron beam is supported at its ends by 2 steel cables. So I always like to draw the picture of this stuff. What is going on? Where is my... Oh, well, we're having all kinds of problems today. There we go. My little tablet was unplugged. What are the odds? Let's try it now. There we go. So here's the steel cable, perfectly drawn steel cable, and then we have our iron beam. And technically, I should draw this, they said supported at the ends. Like this. Oops, got a little too carried away. And we'll make this the ceiling. So this is 9 meters long. Okay. And then my iron beam has a mass. That's our iron beam. I'll make it look like iron. We'll do this. And that weighs 30 kilograms. Okay, and then it says, what is the breaking strength needed for each cable if a 50-kilogram worker must be able to stand safely anywhere on the beam? So we're going to assume that this 50-kilogram worker stands on one end of the beam all the way at the end. Here he is working, and he's 50 kilograms. So this is really a torque problem. So if you guys don't remember this, in order for, so there's 2 types of torque. If I have a fulcrum here, if I have something here, and then on the opposite end, I have the weight of the worker. That's going to be the mass of the worker times G. Now there's some extra stuff too. The maximum force on the 2 cables, we have to consider the beam as well. So let me think about how I want to word this. There's the length of the beam, right? So we have to consider the length of the beam, which is 9 meters, right? And so the sum of all the torques have to add up to 0. In other words, there's going to be a torque going this way, and then if you think about it, there's going to be a torque going this way, and then the formula for torque is just going to be the force applied times the radius, which is really the distance. So depending on how you're looking at that, and if it's a beam, you're going to have the force obviously would be the mass of the beam times gravity. So let me write this out a little bit. So we'll call this the torque of the beam. And so we're assuming that each cable will support the weight of half of this. So you would say 1/2 times the length of the beam times the mass of the beam. Whoops. Times the acceleration due to gravity. And so this represents the radius, this represents the force, if we figure the torque of the beam. But then also, there's an additional torque where there's a torque due to the worker. So now, in this particular case, we're going to assume that the worker is the full length of the beam, right? So that would be the length of the beam, that's our radius right here, times the force, which will be the mass of the worker, times the acceleration due to gravity. Okay? And then the other thing we have to think about is tension. So there's tension on the cables. And the tension on the cable that remains, is going to counteract But if I think of all these things, these are all the different torques and forces. So there's tension on the cable. This is the mass of the worker. This is the length of the beam, right? So we have LB equals this stuff. This is the mass of the beam. And so all these torques have to add up. In other words, the sum of all these torques would be equal to 1/2 times the length of the beam times the mass of the beam times the acceleration due to gravity plus the length of the beam. But now we're going to consider the force applied by the worker, so that's the mass of the worker times the acceleration due to gravity. And then we have to subtract the length of the beam times the tension. That provides another torque, right? So remember, if I choose one side to be positive or negative, the other rotation would be the opposite. So there's two ways you can set this up. These first two could be negative, and the last one could be positive, or we could leave it the way we are. But basically, the cable that's remaining is going to apply a little bit of torque in the opposite rotational direction. And so, and I got to think this through. I'm not quite sure if I put the worker on the right side of the beam. But anyways, the math will work out. But all this stuff has to equal 0. Okay. So then we know everything except for the tension on the cable. That's what we have to solve for. So this is the tough part, I think. All right. So what I really, let me write this. I'm going to write this over here so it looks a little better. Minus the length of the beam times the torque or tension of the cable. Okay. All right. So I'm going to just start, and all of this has to equal 0. So what I want to do is I want to solve for TC. In other words, I got to get TC by itself. So I'm going to subtract 1/2 LB MB G, and then I'm also going to subtract 1 LB MW G from both sides of the equation. So now I'm just doing algebra. Then we'll plug the numbers in. So we're going to say 1/2 length. And you could, if you're one of those people that prefer to just plug the numbers in and then just move the numbers at the end, that's fine too. Oops. And this seems like a lot. It is, but it's your final exam. Minus LB, I don't know why I put the 1 there, but you guys know it means this, right? So then what I end up with is I have negative length of the beam times TC is equal to negative 1/2 length of the beam, mass of the beam, times G minus length of the beam times the mass of the worker times G. So now what I'm going to do is I'm going to divide everything by negative LB because every term has LB in it. So that we get the tension of the cable is equal to positive 1/2 MBG plus, because this cancels with this negative cancels with this negative cancels with this, and this cancels with this, plus MW times G. So let me just double check and make sure I have all that right. Double checking my math. Okay, cool. And then we just plug in the numbers. So my tension on my cable is going to be equal to 1/2 times the mass of the beam, which was, I forgot what it was, 30 kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared, plus 1/2, or not 1/2, plus the mass of the worker, which was 50 kilograms, also times the acceleration due to gravity. And that's meters per second squared. Okay. And if you plug that in a calculator, you get about 637. Now, I know that the textbook does some stuff with significant digits, and their rounding seems a little wonky, but this is multiple choice. But now this is the tension in the cable, okay? And we needed to find a safety factor of 7. So when we have to find the safety factor of 7, that means I'm going to have to take this tension and multiply it by 7. So if I say 7 times the 637 newtons, then that gives me the minimum force would be 4,460 newtons. So this is the final answer. So a lot of times when they build bridges, like the bridge we have in town that goes over the railroad, they go, well, how much weight can be on this? And I don't know if you guys remember me explaining this when we went over this, but it's been a while, so I'll explain it again. When they build that bridge, they go, well, what's the heaviest load a semi-truck can hold? What's the most amount of weight that'll be on that bridge? And then they do all the physics to see how they need to design the bridge to hold that much weight. But then they go, but to be safe, we're going to do a safety factor of 5 or 10, depending on whatever they feel is the safest amount. So when they do that, it ensures that you never breach that. In other words, if the most amount of force the bridge can hold was 100,000 newtons, but they had a safety factor of 5, they would build the bridge to hold 500,000 newtons. Does that make sense? You just multiply it by the safety factor. Okay. Okay. Whew. Now remember, and even I'm tired. Where is my mouse cursor thingy? All right, here we go. Do you need me to zoom out? Does everybody have that written down? Because I'm going to stop recording.